Good morning.
Good morning, sir.
Actually, we were trying to adjust the board and all. I think this part is visible to you. It's better, like as I told you that why, while using while doing class on your mobile, don't hold your don't attend the class on a vertical manner. Rather, you do it like in this way. That will give you the maximum coverage of the board. Okay. Hello, Aniket. Am I audible?
Yes, sir.
Okay.
Yes, sir.
Okay. Well, then I'm just going to start the class. So we were discussing deterministic finite automata. I think this is not visible. Visible? This is visible to you? Hello?
Yes, sir.
Yes, sir.
Okay. Okay, fine.
सर प्लीज डू वन मोर थिंग इनको बोलिए अटेंडेंस बीच में करेंगे बहुत लोग लैब कर रहे हैं क्लास बहुत लोग ज्वाइन कर रहे हैं ये अनाउंस कर दिए हम कभी भी अटेंडेंस ले सकते हैं
Okay, as far as attendance is concerned, we can take attendance at any time randomly. So be attentive in the class, okay? Fine. So, we have done what is DFA, then the number of DFA acts as even number of zeros and acts as even number of ones. And then certainly in your tutorial you have done certain set of problems for which you have to draw a DFA diagram. So next I'm going for just giving you few examples and then some observation out of it. Say this is my 0, 1. This is my first language L1. X has occurrence of 110. The next language is 01 star. X has occurrence of 101. And then L3 is these are the three languages. The L1 language says that all the strings of is combination of 0, 1 and it has an occurrence of 110. That means there is some sort of substring 110 which occur in any part of this string. Whereas L2 is again string of zeros and ones, this language, and it has occurrence like substring as 0101. Then L3 is actually, you can see that what we are looking for is that the string must have the occurrence of 110 as well as 101. So that means both the substring should be the part of the string. So these three languages are defined, and suddenly what we can see here is that when we look for L1 and L2, and when you go for L3, then L3 is nothing but intersection plus. Okay? So I can define L3 as that it's the intersection of L1 and L2. Likewise, I can define L4, which could be L1 union L2. I can define L5, which is L1 complement intersection L2, something like this. Or I can define so many languages out of the combination of these three. So now the question is, individually whether these languages are regular or not. Regular means that can we construct machine for this, can we construct for machine for L2, can we construct machine for L3, and if we can construct the machine for L3, then that means the language in the intersection of two languages, I can actually construct a machine for that. So in that case, I can say that the intersection of two languages be regular, or AFA can be constructed. So obviously, if you look for L1, it is very simple to construct that. Certainly, I can go for this, then I can go for this, then 1, 0, and this is my final state. Okay, as many times I can go for 0 and 1 here. This is my initial state, so I can say Q0, Q1, Q2, and this might be Q3. And if for 1, then certainly I can write as many zeros you have, you can go for it. If I'll get 0 here, then I can come back at this place, then I'll be going for this 1, 1. If I get 1 here, certainly as many ones I can get, I can be in the same state, because what we require is 2 consecutive ones. And then I'll move to this. So this diagram is actually a DFA diagram out of this language L1. Similarly, I can draw a diagram for 101 also. I can write this, then 0, then this, then 1. So this will be my final state. This is my initial state. I can write Q0, Q1, Q2, and Q3. As many 0 ones comes will be the part of this final state, because we have already achieved the substring 101. Now the question is, if I get certainly as many zeros are coming, I will be in the same state, whereas the moment I get a 1, I can switch the state, because I am looking for 101. This is my substring. This is my substring. So for this Q0, I have defined 0, 1 transition like this. Now the question is, if Q1 is having input as 0, then I can switch to Q2. What will happen if it is 1? So as many ones comes, I make it in the same state. There is no problem in that, because I am looking for first one to encounter. This is what we have. So that means I can conclude that L1 and L2 are constructed two machines out of it. Now come to the L3 part, and certainly so what we are looking for 101 and I need both the substring to be the part of the language. Okay. Suddenly, what in that case, what will happen is that while constructing your DFA, what you need to do is very simple. That you start with Q0, and then you look for first. I can look for 110. Then I can go for 101. This might be the first case. The second case is I may get 101 first and then I will get 1105. So either of these two transitions will be the part of the machine. That means there will be, while going for this part, you will be having one set of transitions. While going for the next part, there will be another set of transitions. So that will be there. Certainly you can see that and this is 10. So while going for this path, there is no need that I will go from this part only. What I can do is that I can switch to this part the moment I get this. That means 10 already I have got. I will be going for the next one to be. Yeah. So your transitions will have a different branch after this, and then you can construct. But the problem with this is that it will be a complex diagram for you. Okay. The idea comes in mind that can we have some closure property of regular languages? Closure property says that whether two languages are given, can we have a union of two languages? Can we have intersection of two languages? Can we have a complement of the languages could be again be regular or not? Like you can go for homomorphism as well, you can go for reversal of the languages as well. When I say reversal of the languages, that means if your language is having this, then reversal says B. So this is your this, and this is this. That is the reverse of the language. So this is what we have. So we look for the closure properties in terms of union, intersection. Even we go for set difference, then complement, and homomorphism. Reversal. So these proposal property, if holds, then solving such problems, that is creating diagram or creating DFA of such languages, which is again the combination of another two languages. That means combination means it will either be a union or intersection or maybe anything out of it. Then it is easy to prove it and it is easy to draw also. Okay, so we'll see later on. I'm just discussing this. So now, what is actually we call it as language with finite elements, or you can say finite set. So what we are looking is something like I can say that okay fine, I just looking for a language which is having 0 0 1 0 1 and then 0 1 1 0. See, this language contains only 3 strings. The first string is 0 0, second string is 1 0 1, and third string is 0 1 1 0. If the question is whether is L regular or not. So the answer is can we draw DFA out of it? Can we draw DFA out of this? So the question is, let us try. Okay. So what we will do is, you know that what you have is 0 0, then I can go for this, I can go for this, and this will give you 0 0. Okay. Q 0, Q 1, Q. This is your final. Now, the problem with this particular 0 0 is that except 0 0, nothing could be accepted. So for that can be done only that suppose if 1 comes at the initial state itself, then what will happen? Suddenly it should not be accepted, or it should not go forward in it. So for that, I'll go for this. So we have 1, then I'll go for this. We have 0, then I'll go for this. Again 1 comes, I'll go for this. If 0, I'll go for this. If anything comes 0 and 1, I'll go for this. And so you can see that I have defined all the transitions for all the state. And it actually accepts only 0 0, not any other state. But in each of these states, when we go for 1 1 0 1, then we land up in some state where actually I am not going out of that state. I am just being in the same state, which is a non-accepting state as well. So this state I can name it as Q3, and this Q3 is known as dead state. Q3 is known as dead state. Because why I am saying dead state? Because whenever any transition comes in this state, it dies. or any number of transitions can take place, but it will not go out from this state. And since this is not a final state, so obviously this is a dead state. So this is what the meaning. So that means I can construct a machine of 0, 0. Similarly, I can construct a machine for 1, 0, 1 also. Similarly, I can construct for this, because it's the same way you can proceed as we have proceeded for this 0, 0. So same way I can proceed for 1, 0, 1 also and this also. Now, the question is that there is no query. Okay, fine. So I'm just moving forward because you don't have any query right now. What I'm looking for is that I need a machine which accepts these 3 strings. That means I need a single machine which can accept these 3 strings. Then I can say that this is regular. Okay. So let us try for that. So, obviously, this is my initial state, Q0. Okay. So I can go for 0. Then I can go for 0. This is. So this is my final state. You can write Q1, Q2. Now I can create a dead state, say D1, and I can go for 0, 1, 1. Okay, so I can go for this. Right? Why I'm not going I'm not going for 1 to dead state? Because the reason is that I'm looking for this also. So in initial state, if it is 1, 0, 1, then I can go for this. Okay, right? So what I do is so if it is 1, then I'll go for searching this 1, 0, 1. So I'll go for 0, 1. So I can write Q1, Q2, Q3, Q4, Q0. So we are going for this 1, 0. Okay. Now, what I am looking for is 0, 1, 1, 0, 1. This I am looking for. Okay. So 0, 1, 1 will be. So I can go for 0, 1, 1, 0, this will be Q6, Q7, Q8, this. Okay. So this is your transition sort of things which can accept 0, 0, 1, 0, 1, 0, 1, 1, 0, 1. Like you can see that when I get 0, 0, I will be going for this 0, then 0, then this. Okay. When I get 10, when I look for 101, then I can traverse from this, I'll be reaching this kind of state. When we go for 0, 1, 1, 0, 1, so if suppose you are in 0, then either you can get another 0, then you can go by this way, or if you get 1, so I'll be going for this way. Except this, anything will go to the dead state. So this will go and 1, 1, 0, 1. Now, what is your task? That for each of these transitions, for which the transitions for input is defined, but it is not defined for all input, because you can see that I have defined 0, 1 for Q0, I have defined 0 for Q3, but I did not define the 1 for Q3. The moment I get 1 for Q3, then certainly it will be in dead state. So it will be in dead state too.
Even we saw the 1 hटेगा, क्योंकि 1 तो हो गया है, वो मैंने फिर जाएगा. This one.
This one.
Yes.
Okay. Yes. Okay. Yes. Yes. So this will not be there, because the one you will be going for this. So Q0 for 0, 1 we have defined, for Q1 0, 1 we have defined, for Q2 0, 1 we have defined. Now this Q3 0, 1 defined. Now Q4 1 is defined. If it is 0, I will be going for this. And if it is 0, 1, I will be going for this. This is 1. Then again we will define this for this also. If we get 0 here, then I can go for dead state 3, 0. If I get 1 here, I will be going for this. If I get 0 here, then I will be going for this. If I get 0, 1. Okay. So this is the diagram, which actually is a DFA diagram. I can say M, and this is nothing but L equals to L. That means the language is 00101, 01101. These three strings to be accepted under this language construct. I have defined a machine N where this machine is actually accepted 00101, 01101. Now, to check this machine whether it is working for you correctly or not, you can take anything, like you can take that 110 if this is accepted or not. If I will go for 110, then suddenly 1 comes, then I will be going for this. If another 1 comes, I will be going for this. Okay?
So there is a question.
Certainly,
can we use just one dead state to the whole machine rather than taking different?
yes. Yes. The question, I think the query is that can we use one dead state for the whole machine rather than taking different? Yes, you can. But why I am using 3 different dead state? Just to have a very simplified diagram. Because once you go for one dead state, there will be so many lines you will be drawing to reach that dead state. So I have just created dead states in 3 different positions, just to include the simplicity in the diagram. Okay, that is very clear. Certainly you can do it for one dead state only. Okay, it does not matter because all dead states will result in the same way. Or further, if you improve this, like when you are minimizing the number of states of this particular DFA, then you will find that these dead states will be clubbed together. Okay. Since we are in early stage, I am not doing that. So I am just trying to give you the idea about this in a simplified manner. Yes. Okay. Okay. Any query on this? You can ask me. You can check this for so many strings. You can check for this, like suppose 0, 1, 1, 0, 0. This. What I did is that I have just copied this part, just change this part. Or even you can check this for this also. Okay? You can see that if I go for 0, then 1, then 1, then 0, then 1, but the moment you get 0, will be this. Okay? So this will not be accepted. Okay? If any of this string except these three is accepted by this particular machine, then your machine construct is wrong. So be careful. May I go forward? So, so that means we can construct the FA of any language having finite number of strings. Okay, so I can certainly I can draw one conclusion that finite length languages are regular. Are regular. Okay. There are two things, like just for your always note that if your sigma is actually an input set, okay, this is a finite input set, then this is one diagram, and there is another diagram is this. Okay? You can say choose your. So my question is that what this diagram is for and what this diagram is for. Okay? So simply you can see that this diagram is for empty string, whereas this diagram is for okay. That means this diagram can actually accept any string out of this sigma. Okay. That means if I write sigma is 0, 1, then sigma star means any string which can be a combination of 0, 1 will be accepted by this convention. So always remember this, that this diagram, this is a DFA, say M2 and M1. M1 is for empty string, whereas M2 is for sigma star string. So any string it can. So that is one.
So there is a question. How can first diagram accept empty string there is no final state? The first diagram that you draw to empty string access कर सकता है उसमें final state नहीं है.
Okay. I think good question. Actually, what I'm saying is, question is this. You know that empty string is empty. That means nothing is there. Okay? So obviously, the moment I go for any sort of any final state you are looking for, so from going from this state to this state requires an input to be there. Okay? The moment input will come, it becomes non-empty. Even if I go for making this final state, then it can take any string out of 0 1. So to actually represent empty string, we are using this because empty string means nothing is there, so there is no input for that. Or you can say, or the best way is that normally we do not do that. I should not go in that. So we have some epsilon or sort of things. We'll discuss on that. Right now, just remember that if I make this state as final state, it can accept any string. If I go for another final state which can go from this to this without having anything, if I go from this to this, then whatever will go will require some input to be there, then it becomes non-empty also. And for your kind information, I have to define the transitions for this particular state also, this particular state also. So certainly in that case, I am not able to define this particular transitions, because the moment I put any input, it will become non-empty.
So what will happen if we will have initial and final same and without any input, 0 1?
What you are saying?
Initial and final same.
You cannot, because DFA says that DFA is a deterministic finite automata. So whenever you talk about any deterministic finite automata, for each of these state, you have to define like transitions for all the inputs. You cannot ignore that. That means, if suppose sigma is ABC, this. So if I go for initial state or any final state, so as many states in between, or even only you have initial state or final state, even if you have all of this, you have to define this ABC for each of these states. So you cannot ignore that part, because this is deterministic finite automata. And for that only we have gone for non-deterministic also, which will take up in later stage. Okay. Hope it is clear for you all.
One student is saying, so is Q0 is dead state?
Is Q0?
Initial state, and we are creating it without the final state, no?
Yeah, you can assume like that only. See, it's not a dead state, rather I can say it's a non-accepting state. Dead state means, like, when I say, obviously instances are like dead state, but it is a non-accepting state, but certainly the dead state is like that only. But since this is the initial state, we are not calling as dead state, rather than we are calling as non-accepting state. Now, just we'll look for some more examples. Say L1, we are talking about x belongs to 0, 1 scala. Last bit of x is 1. This is one language. Another language, say L2, x belongs to 0, 1. Second last bit of x is 1. So such languages could be like in first case what you are looking for is the last bit is 1. That means whatever string you are looking for, the last bit should be 1. That means last input is 1 that we are looking for. Generally, how to do that? That you know that I can go for this, say I am going for N1, that means L1 is L of N1. I am just looking for this. So as many zeros you can is fine for me. And then the moment I get 1, then I'll go for minus 2. Now the question is, obviously as many ones comes, it's fine for me. Then 0 comes, I'll come back. Okay. So you can see that this actually gives you a language where actually last bit of x is 1. Right? Yes. Now the question is, so this you can say Q0, I can say Q1. Q1 is your final state, whereas Q0 is initial state, and we have defined transition for 0, 1 for each of these. That is fine for me. So this signifies the first language. But how do you do this L2? So I am looking for N2 to be constructed. Okay, that is machine N2. Fine. So what we are looking for is second last bit of x is 1. That means I am looking for string of 0, 0, 1, 0, 0, 1, 0 like this. 1, 0, 1, 1, 0, 1 like this, or 0, 0, 0, 0, 1, 0. So what I am looking at, the machine should accept such string, where actually I am looking for this to be. So second last bit should be 1. This is what my criteria is. So, how do you do it? So, certainly I can go for, like, say, initial state, then Q0. What we are looking is that we're looking for 1. So, as many zeros comes, I will be in the same state. And then 1 comes, then 0 or 1 comes, I will be the final state. Okay? Now the question is, I I have defined 0, 1 for this. I have defined 0, 1 for this. But what if anything comes after that? So what you want is that last bit, second last bit should be 1. Will it work? It will work. So this could be your DFA diagram for the second language line 2. And just remember always that when I say that some given languages, I am telling you that to construct the M2. So always remember that what constructing this is okay. You have to define the you can say components of the machine as well. What I am saying is that M is say Q sigma delta Q0 M. So while defining, like when you construct this machine, there is a parallel things which you could also do that you define Q for this particular machine. To define sigma, sigma is already there, but you have 0, 1 in sigma. Yeah. Sir, if you be input 111, it ends to Q1 state, but it has second last bit as well. Okay. 1, 1. Yeah. Can't we remain on Q2 if 1 is the input? Certainly, there is one query that can't we remain on Q2 if 1 is the input. The problem is that if I go for it like this, then if suppose your 0, 1 is the last 2 bit, then it will from this, for taking 0 it will come to this, by taking 1 it will be in this, so this is not the second last bit. So this is also not correct. So we cannot take this part. Okay, what is next? So this can't be done. Next is take loop of 1 in Q2. Not possible. I think it should have 2 end states after Q1. 1 for input 0, 1 for 1. Okay, so that means there is a problem in this. Okay, so this diagram is wrong. This is good. So I'm looking for such queries because this is not the actual machine for this. Now come to the actual machine. What we can do in this is actually you have to develop a logic for this machine because simple logic may not work. The logic is very simple, that we have to create states in a way that I can get 1 as second last bit. Okay, fine. So what we have is that suppose what I am looking for is as this string will have any length, and then there is last two bits are there. Okay, so this is my string. This string of any length is there. I am looking for last two bit. So what is the like what sort of probable things could be? This last two bit could be 0 0. This could be 1 0, or say I can write 0 1. This could be 1 0, and this could be 1 1. Okay, this is what we require. That fine. So what we do is, okay, fine. This can't be accepted, whereas these two may be accepted. Is that okay? So this 2 can't be accepted, this 2 can be accepted. So we'll refine the diagram in a way so what logic we'll develop is that we'll start this particular logic from the initial 2 bits. That is what will happen. I'll be going for this, say Q0. If I may get 0, I may get 1. So this is there. Okay, fine. Now the question is, if I get zero here, so I'll be landing up in 0 0 stage. So what I'm saying is this is Q1, and I'm saying Q1 is nothing but Q1 states 0 0. Okay. If I get 1 here, so Q2 is nothing but 1 1 state. Okay, fine. The another thing is which will come is that if I get 0 here, 0 comes like this. If I get 1, then I will be going for 1. So this is my Q3, and this is nothing but 0 1 state. But when I land up in this, I'll be getting 0 1. Okay. And this is 1 1, so this is 0. So this will be Q4, and this Q4 nothing but it says 1 0. This is what we have. Okay. So then we have what we have in this is that certainly what we are doing is that at a time I am scanning this 2 bits, then I will be scanning 2 bits again, then 2 bits again, then 2 bits again, then 2 bits again. So my scan will be 2 bits again because this machine is like that only. So now the question is, first of all, define all the possible transitions which can take place. See, what I am here is Q3. If I get 0 1, so 1. So now the 1 is the last bit. If I get 0 here, so it becomes 1 0. 1 0 is this state. So what I do is that I go for this. Fine. So it will go for this because this is 1, this is 0. What will happen if it is 1? So it will go for 1 1. So you can see that if it is go, so it will go for 1. Isn't it? Now for this, if it gives you 1, so it will be 0 1. So it will go for this. If it is 0, then it will land up in 0, 0. So I will be going for this. Okay? This is my diagram, which will take care of that. Obviously, so your final state would be, this will be your final state, and this will be your final state. Is this a correct diagram or not? Is this a correct diagram or not? Just think about, there is a problem in this diagram. No, sir. Yes. What is the problem with this diagram is that the moment I go for this, 1 will be accepted. So what is required to be done in this case is very simple. I'll just extend this for a bit. What I'll do is, I'll go for this, then I'll go for this, and I will go for this, and like this. So I'll go for this and 0. Fine? If I'll do this, it will be working. So what is happening is, this is Q0, I can say, I can write anything like here. Maybe any state, Q10, Q11 sort of things I can write. Now the question is, will this work?
You don't say input.
So what is happening is 0, 0 will land up in this, 1, 1 is lined up in this. So obviously when we get only true like 0, 0, it will land up in this. Now, for this you have defined 0 and 1, but you have not defined 0, 1. So 0, 1. So if it is coming 1, so it will go to this. If it is 1 here and 0 comes, it will go to this. Sorry. I think probably this will work. Is that okay?
Is there need of Q10?
Yes. Without this, you cannot, like in previous case, like you can rename it. Like, no more icing. Q0, Q1, Q2, Q3, Q4, Q5. You can rename like this, there is no problem in this. Can we just make Q1 the initial state and remove Q0, Q10 and Q11? No, I cannot. Because we have seen in previous case it was like that only. Only the thing is, in that case, if suppose if you don't have this particular state and only 1 is input, then it will straightforward, it will go to here and it will accept it. Just 1, like suppose your string is 1 only. If string is 1 only, then certainly if this state will not be there, then this will line up with the final state, which is wrong, because we need second last state is 1. Okay, so this is what it is. Fine? Instead of Q1 in between, if Q0 directly goes to Q3, it will work the same. No, sorry. What we are saying is Q1 in between if Q0 directly goes to Q3. See, if you are doing like this, your one query is, can we go directly to this? Okay. Since this is a non-final state, only the thing is, sort of smooth tracking, it will be always good that you put it here. Yeah, I think probably when we go for minimizing the states in DFA, it may be the case that this Q3 may be not required. Right now, just for simplicity, we are keeping this. Certainly, let me tell you 1, 2, 3 observations out of this DFA. One thing is very sure that you can create any number of DFA out of one language. Just remember, what I'm saying is you can create different DFA out of one language. Different DFA, more states are having the same language to be accepted. Another can have minimal number of states still accepting the same language. Another people can go for another number of states still accepting the same language. But the vice versa, if you look for, any machine always accepts unique language. So one machine cannot accept multiple languages. It will only accept a single and unique language. So one machine is only for one language. Whereas one language can have multiple machines. Okay, so that part is there. Another thing is, in case suppose, while defining the logic for a particular machine, certainly everyone could think of in a different manner and could actually go for different set of machines. And certainly you are landing up in more number of states rather than minimal number of states. That is correct, DFA is correct, but we always look for minimal number of states to be part of the transition diagram. The reason is very simple. This machine actually talks about logic of the language. But when you convert this particular thing into a hardware, and certainly each of these requires so many gates to be there. And as many gates will be there, suppose suddenly as minimum as possible gates will be there, then certainly your hardware will be a simplified hardware. More number of gates will be there, then your hardware or chip will be complex in nature. So our motto, our aim is to construct a machine for a particular language with a minimum number of states, so that when we translate this into a hardware, it will have a simpler you can say constructions rather than complex. So that is the idea why we look for minimal number of states to be there. So I think that is there. So unique machine. What is?
For any two vector language, L1 and L2, L1 even L2 is not vector.
I will come to you. Let me inform you that union of any two languages is always regular, because we'll come to that part also, because I'll just go for closure properties of the regular languages. Then we'll see that there are some properties which holds, and there are certainly all properties could not hold for many sort of languages. As far as union is concerned, yes, union of two languages is regular. Okay. So suppose this is L1 and this is L2. When I say L3, L3 is union of L1 and L2. L1 union L2. So whatever I am defining this L3 language will be this. ARM construction machine of L3, which is a unique language. Okay? That language is like that it actually reflects the union of L1 and L2. But I am not constructing L1 and L2 like if you are constructing a machine for L3, it is not the case that it will accept both the you can say we are not constructing machine for L1 and L2 differently, or it is not in a like there is like we are constructing a single machine L3 which accepts language having strings which actually reflects that it is union of L1 and L2. Okay? Is that fine? Yeah. I think we can switch from this part. Is it okay? Okay, I think you can take attendance.
So everybody comment their
क्या वही है ना कि तुम लोग
कमेंट कर लेते हैं
कमेंट कर लो हाँ बोल दो करने के लिए
everybody comment their roll number.
For attendance, everybody should be writing their roll number in comment section only once.
तो 85 हो गए 80 से ऊपर पूरे सेशन में नहीं गए 55 आ गए इसका
Okay, sir will be further taking few more topics. So after attendance, you should not be leaving. All those people who are writing their roll numbers will be cross-checked once more. Microphone. नहीं वीडियो बंद करके माइक्रोफोन Okay, for a few minutes we are switching off video and microphone. You stay there, session will be continued, and in the meanwhile you write your roll numbers.
Okay, so we'll go for I'm just giving you say L3, I am giving you as homework. Okay? The language is the similar way the previous language was saying that the second last bit is 1. What I am saying in this is that can you draw a diagram, construct a diagram, DFT diagram, where actually what you are looking is the 8th bit from last is 1. It can be anything, like you can go for 4th bit, 5th bit, 6th bit or something like that. This is just have a look on this and try to do that. You can submit this particular problem solution in a tutorial session. Okay, so that's it. I think last time also I have given you one assignment to prove that the language having even number of zeros and even number of ones, and prove that the language is equivalent whatever you are having machine. That means that was the case. Suppose did you submitted this part into a tutorial, last tutorial or not? So please submitted this also. That is the same example I am giving you. We will be using some induction, proof by induction, and you have to prove that. Okay. So now, so what we are looking is the closure property of regular languages. Then suppose we have L1 and L2. Then union says that L1 union L2. So say these two are regular. So whether it is regular or not. So closure property says yes. If L1 and L2 are two regular languages, then union of these two languages will also be regular. This is what we have. Say, now go for, you have L1. So L1 is nothing but L of M1, and L2 is nothing but L of M2. And I am defining M1 and M2 like this. Say Q1 sigma delta 1 and Q01 and F12. Well, I am defining this as Q2 sigma delta 2. Say P01 and F2. Yes. So this is what we have. So now what I am saying is that L1 and L2 are two regular languages. So certainly we can have some machine M1 which can accept this L1. We can have machine M2 which can accept this L2. Machine M1 and M2 certainly will have components like this. Q1 sigma delta 1 P01 F1. Q2 sigma delta 2 P01 and F2. What I am saying in this way that, but in this machine this Q1 number of states will be there. In M2 there will be Q2 number of states. So this is a set. So number of states will be there. Certainly it may not be the case that it will be the same. It will be different also. Then you have two different transitions, delta 1 transition for all the transitions of M1, delta 2 reflects this M2. This is initial state of M1, this is initial state of M2. Final state set of M1 and final state set of M2. This is what we have. Now I am trying to define, say, L3, which is nothing but L1 union L2. So that means I have L3, which is nothing but L of M3. And this M3 is nothing but Q sigma delta, say Q0 and F. Okay? This is what we have. Now, to prove or to have that this L3 is also regular, which is nothing but the union of L1 and L2, what we need to prove is that can we represent Q in terms of Q1 and Q2? Can we represent delta in terms of delta 1, delta 2? Q0 in terms of these two, F in terms of these two. If I can do that, then certainly I can conclude that this is regular and DFA can be constructed. Because we have two DFAs, only the thing is merging is required, which we can do that. So let us do that. So I think this is clear. May I just remove this the upper part?
L1 और L2 के सिंबल्स भी डिफरेंट हो सकते हैं, सिग्मा 1 और सिग्मा 2 भी हो सकते हैं।
नो,
एक 0 1 में हो और एक
नहीं, वो नहीं हो सकता। Always sigma will be same for both. I think sigma will not be different. No, sigma will not be different. Sigma, like input string will be same. Input string, input alphabet will be same. Symbols will be same. Okay. So what we have is now is that what is Q1? That means I have to define what is Q. So it says Q is nothing but this Q1 cross Q2. Okay. Fine. So if I say that I have Q1 as Q0 1, Q0 2, Q. Sorry. Q1, Q2, and this is Q2 is I can write P1, P0, P1. P2. I can write like this. Okay. So what this will be? This will be like this. Q0, P0, Q0, P2, X. Okay? So it's a Cartesian product of all the states of this Q1 and Q2. That will be right. So this is my first one. The second one is that sigma, I told you that all three will be same. So whatever input symbols will be there will be the part of all three. Now the question is, and very simple what we have is that if you have P0 is initial state for machine 2, Q0 is this. So obviously when we write Q, I can write this as Q01 for this. So Q01 is nothing but this. Q0. Right? This is what? The combination of initial states of machine 1 and machine 2 all together. So this is what. Now the question is, what is Obviously, this F will be F1 union F2. Okay, this will be there. Okay, this is there. So now only the thing is left is how to define this delta. So delta says that obviously if I define delta as this Q0, P0, say A, if I define like this means delta 1 Q0 A, delta 2 P0. This is what this. Okay. Q0A, P0A. So obviously delta 1 transition is for machine 1 and delta 2 transition is for machine 2. So this particular transitions can be defined as this. So it can take either of this. Okay. That this shows that this can take either of this. It can go by this also, it can go by this also. Okay. So this is what we have. So what we have seen here is very simple. That obviously the question is, what is the accepting state for this? Oh, sorry, this is not union, this is cross. Okay? This is cross. So while defining the final state, X belongs to what we have is we can say sigma star or this. So this can be defined as defined like this. When we say as this, then this is nothing but P, or let's say Q, P. You have that means all such combination of P and Q and P, which are the final states of machine M1 and M2. This could be all such will be that such that Q belongs to F1 or P belongs to this groups. इसका मतलब simple है. The meaning of this is very simple. That suppose Q10 and Q15 say this is my F1. This is the example I am giving. And suppose F2 is P19 and P10. Suppose this is what. So that means this F could be any combination. And it is not necessarily that always these two combinations must be a final states. I can write that I can have P19 say and Q5. This is also my final state. Why? Very simple is that just see P19 is actually one of the final states. So it can take any combination with anybody. That's why I am saying all. So all such combinations which have either this is final state or this is final state will be the element of this final state, F, the union final state. Okay? So this is what union talks about. So this way what we have seen is that we could be able to define all the elements of the machine M3 in terms of machine M1 and M2. So hence I can conclude that it's a combination of two machines. That means I am just merging two machines here in one machine. So I will conclude that union is also regular if the two languages are regular. Okay. So that is what we conclude out of. Is that clear? Sir, if L1 and L2 may have different symbols, now, so that means union is confirmed that it is regular. Now the question is, what about this L1 and L2 are regular? Is regular or not? Can anybody tell me whether it can be regular or not? Why I am saying that certainly that means what? You have to define L1 and L2 machine. Then when you go for L3 and L1 intersection L2, so obviously we have to define L3 as machine L3 of this. So whatever M3, then you have to define all the components of this intersection part in terms of these two machines, and if actually we can do that, then we can say that intersection is regular also. Let me tell you that it can be done, it can be proved right now itself. Like that's, I think in the very first class I told you that just go through the set theory and other parts, some elementary mathematics I suggested you. Then you can find that this. Then I can easily prove that this intersection is also regular. The reason is why we have just seen that L1, which is x belongs to 0, 1 star, x has occurrence of 1, 0, 1. We have seen that this is regular because we have DFA for this. If I go for L1 complement, then what we have is that I am looking for languages that x has not the occurrence of 1, 0, 1. And I can define like this. Simply what you need to do.
It's not
What I am saying is x belongs to 0, 1. X has occurrence of 1, 0, 1. What I am saying is L1 complement is nothing but x belongs to 0, 1. That x has not the occurrence of 1, 0. This can be achieved very simply. Whatever diagram you have constructed for this particular L1, what you do to get L1 complement, that means this is say M2. So you can get this particular machine just reversing the non-final states, making non-final state as final states and final states as non-final states. That means whatever diagram you have got, whatever DFA you have, what you do is that make final state as non-final and non-final state as final. If you do that, you can get the complement of the language. Okay? So that means L1 is regular, then L1 complement is also regular. This can be established very easily. Okay? Fine. Once I can establish this, so what we have is, we have that L1 and L2. So we have L1 union L2 regular. These two are regular. Now L1 complement and L2 complement, this is also regular. So now the question is, what about this? I can express this as L1 union L2 complement. So I know that the union is regular, so this 2 is regular. The complement is regular, so this is regular, this is regular. 2 regular languages, the union of these 2 is regular languages. If this comes as one language, the complement of that language is again regular, so hence this is regular. Okay? So this can be. So intersection can also be regular. Right? That's it. So I'll just stop right now. We'll continue in the next class with closer proof. Okay? Fine? Thank you.